right, thanks for tuning in. This is the final section in this course, section 5.5, which is about the technique of substitution. So in this course so far, or at least in this last chapter, we've been looking at antiderivatives, and we've seen not very many techniques for finding the antiderivative thus far. In fact, we've only really looked at something called the power rule, which is when you have a power of x, and we know that the rule there is we do the opposite of what the derivative does. So we increase our exponent by 1, and then we divide by that same exponent. We've also seen how to find the antiderivative of our trig functions and exponential functions. We know that the antiderivative of 1 over x is ln x. But other than that, we haven't really found the antiderivative of more complicated functions. And so analogous to with the derivative, when we were learning how to take the derivative of products or quotients, so when things are being multiplied or divided, we found that it wasn't just as simple as taking the derivative of the two things separately and then either multiplying or dividing them. We had to use these more complicated rules called the product and quotient rule. And so it's sort of the same idea here with antiderivatives when we're going backwards from the derivative. If we have a function where something is being multiplied or something's being divided, and we're not just talking about multiplying by a constant or dividing by a constant, we're talking about, you have two functions of x which are being multiplied or two functions of x which are being divided, then what ends up happening is you have to use a more complicated rule in order to find the antiderivative. It's not as simple as just separately taking the antiderivatives of the two functions and then either multiplying them or dividing them. So this technique of substitution is going to be the only technique of integration in this course that you learn. So basically you'll either be able to find the antiderivative using the power rule, and if not, you're going to have to use substitution. So at least you'll know when you have to use it. And we're going to illustrate this method using an example. So our first example here, we have the indefinite integral of x squared over 4x cubed plus 2. So I'm saying it's the indefinite integral because there's no bounds on the integral. So remember this notation here, this indefinite integral, the result of it is just the antiderivative function. So the result of this integral is going to be a function. So the first thing that we want to notice is, why do I need to use substitution for this integral? And so looking at the function, there's two things being divided. It's an x squared divided by a 4x cubed plus 2. So that's a real hint that we're going to have to use substitution, because I can't just use the regular power rule because this is not just a power of x. So your first step, step 1, when you're doing it's called a u substitution, you let u equal the inside or the exponent of the more complicated part of the function. Okay, so let's try to identify what's more complicated. We have an x squared, and then in the denominator we have a 4x cubed plus 2. So even though it's not crazy complicated, that 4x cubed plus 2 is the more complicated part. So we're going to let u equal 4x cubed plus 2. Okay, the next part of step 1 says find du dx. So we want to find the derivative of u with respect to x. So du dx is going to equal 12x squared. And then the next thing it says to do is to solve for dx. So what we would do here is we'd say, well, we know that du, if we multiply both sides by a dx, we know that du is equal to 12x squared dx. And so then we would get that dx, if we isolate for it, would be 1 over 12x squared du. Okay, so I like to write it that way. And so we've solved for dx. We know what dx is equal to in terms of u and du. Step 2 then says to substitute u and dx into the integral. And now our integral should be entirely in terms of u. So let's try this out here. I have the integral. Well, my x squared is still going to be x squared. I didn't do anything to that. But my denominator, this 4x cubed plus 2, I've actually called it u up above. So you see here, we've actually called my denominator u. So that means I'm going to say my integral is of x squared divided by u. Now the next part of the integral is this dx term, right? This dx term is what follows. But we know that dx is equal to 1 over 12x squared du. So we're going to put that in for dx. So this is times 1 over 12x squared du. Okay, well, let's see what happens here. This x squared cancels on the top and the bottom, and I'm left with this integral of 1 over 12 times 1 over u du. And so this means that we've done everything right. When you substitute your u and your dx into your integral, as long as your resulting integral is entirely in terms of u and du, you haven't made any mistake. If your x's can't cancel out and you can't rewrite your x back in terms of u, then that means you probably made the wrong substitution, which is okay. If that happens, you just go back and you try something else. So once you substitute in, your integral should be entirely in terms of u. And often, what I like to do is I like to actually pull out that constant, that 1 over 12. And so it's 1 over 12 times the integral of 1 over u du. And so this resulting integral is much easier to deal with. You know, before I was trying to find a function that has derivative x squared over 4x cubed plus 2. And it's not really easy in your head to think about a function that's going to have that as its derivative. But now I want to try to find a function that has derivative 1 over u. Well, we know that the natural logarithm ln has that as its derivative. So, oh yeah, sorry. I actually didn't do all of step 2 yet. So step 2 says to substitute u and dx into the integral. And then once you've done that, you want to solve the integral in terms of u. So this is really important. You want to find this antiderivative, which we just said is equal to 1 over 12 ln u. I'm using the absolute value of u so that it's defined, because we know ln can't take in negative numbers. And then I want to put plus a constant, right? Because we're finding the most general antiderivative here. So I've solved my integral in terms of u. Now one thing, a common mistake that I see that tends to happen in substitution is that you'll get your integral all simplified down to this 1 over 12 integral of 1 over u du. And then what I often see is students putting back in the value of u, so putting back in that 4x cubed plus 2 before they've found the antiderivative. So you don't want to do that. You want to keep the u in there because the u has made your antiderivative easier. It's made your integral easier. So until you find the antiderivative in terms of u, you shouldn't be plugging back in your x's because the x's are just making it more complicated. So keep the u's in there until you've actually solved your integral, which is what we've done now. So the final step is to substitute back in your u function. So you want to put your x's back into your final answer. So we're going to get that this is equal to 1 over 12 ln of the absolute value of, so our u value was 4x cubed plus 2. Okay, that's a messy plus sign, but 4x cubed plus 2. And then plus a constant. And if we wanted to check our answer now to see whether or not we got it right, let's see what would happen. So let's check our answer. So because we said this is the antiderivative of our function, that means that when I take the derivative, so d by dx, of this function, this 1 over 12 ln of 4x cubed plus 2 plus some arbitrary constant, if I take the derivative of this, I should get back my original function, that fraction function. So let's see what happens. The derivative of this would be 1 over 12, and then I would take the derivative of the ln, which is going to be 1 over the inside of the logarithm, so 1 over 4x cubed plus 2. But then it's the chain rule, so it's multiplied by the derivative of the inside, which is 12x squared. And then the derivative of plus c is going to be just 0. So let's actually just write that in. So I'd have plus 0. Okay, so let's simplify this a little bit. My 12 and 12 are going to cancel, and so I'm left with x squared over 4x cubed plus 2. Okay, well, let's go up above. That is exactly our original function here. It's x squared over 4x cubed plus 2. So that means we actually got the antiderivative correct. Okay, so let's work through another example. We want to find the antiderivative, so the indefinite integral of the square root of sine x times cosine cubed of x dx. Okay, so we need to decide what our u is. So I have to do this off to the side. I say let u equal something. Okay, so our rule for finding u is we want to let u equal the inside or the exponent of the more complicated part of this function. So I would definitely say that the more complicated part of these two pieces in my function is the square root thing, right? So the square root of sine x is more complicated than cosine cubed of x. And so I want to let my u be the inside of the square root function. So I'm going to let u equal sine x. Okay, so then my du by dx, which is the next thing that I want to find, is my derivative of sine x, which is cosine of x. Okay, now I want to solve for dx. And so I end up getting, moving stuff around, I get that I'm going to get that dx is equal to 1 over cosine of x du. Okay, so then the next step, step 2, is to substitute this into my integral. So I now have the integral of the square root of u, because I've called that sine x u. And my cosine cubed is going to just stay as it is right now. So cosine cubed of x. And for dx, I'm going to plug in 1 over cosine of x dx. Okay, well, that means that one of my cosines is going to cancel on the top, so I'm left with a cosine squared of x. So I have the integral of root u times cosine squared, cosine squared of x dx. So we might think, okay, well, we've made a mistake because our integral is now in terms, that's not dx, that's du. I apologize. I made a mistake there. So we might think that there's a problem now because our integral it has x's and u's in it, which is not good. But cosine squared of x, there's actually a trig identity that we know for that, right? So let's think about this. Our u that we've chosen is sine x. We have cosine squared of x there. We don't want the x to be there. We'd like it to be a u. So if we could rewrite this cosine squared of x in terms of sine x, then we would be able to replace it with some u's. So cosine squared of x is equal to 1 minus sine squared of x. So that's sort of the only trig identity that you would be expected to know in this class is sine squared plus cosine squared is equal to 1. But if it's equal to 1 minus sine squared x, we know that a single sine x is u. So this is 1 minus u squared. So what we actually have here is the antiderivative. We're trying to find the antiderivative of, I'm going to rewrite this square root as a u to the 1/2. And this cosine squared of x is actually equal to 1 minus u squared. And so now my integral is entirely in terms of u. So we're almost able to find the antiderivative. The next thing that I'm going to do, I'd like it to just be powers of u so that I can use the power rule. So I'm going to multiply this u to the 1/2 through. So I'm going to have u to the 1/2 minus, well, u to the 1/2 times u squared, you add the exponents. So I'm going to have u to the power of 5 over 2 du. And so now this integral is really simple. It's just going to be powers of u. So I can use the power rule to find the antiderivative. So for u to the 1/2, its antiderivative, well, we increase the exponent by 1, so it becomes u to the power of 3 over 2, which means it's going to be divided by 3 over 2 or multiplied by 2 over 3. Minus, for this u to the 5 over 2, we increase the exponent by 1, so it becomes u to the 7 over 2. And it's going to be multiplied by 2 over 7, which is the same as dividing by 7 over 2. And then plus a constant. So the last step, the final step 3, so we found our antiderivative, but we want to now plug back in our original choice of u. We want it to be in terms of x, our final answer. So we're going to have 2/3, and then we're going to have sine x to the power of 3/2. Minus 2 over 7 sine x to the power of 7 over 2. and plus c. And if you wanted to check your answer, you would just take the derivative of this and see that you get back that original function, that square root of sine x times cosine cubed of x. Okay. Now the next note is that sometimes if you let u equal the inside of the more complicated part of the function, it's not going to work. So what's going to happen is you're going to have an integral that is in terms of u and x, and you're not going to be able to do like the trick that we were able to do up here where we could rewrite this cosine squared in terms of sine. So sometimes your choice of u is not going to work. If that happens, so if choosing the inside or the exponent of the more complicated part does not work, your next choice of u, so you should only do this second, but your next choice of u should be to take the entire complicated part of the integral. So we're going to work through an example to illustrate this point. So looking at this first integral, so I have ln of root x divided by x. And if I were to say what's the more complicated part of this function, you'd say, okay, well ln of root x is the more complicated part. So I might start off by saying let's let u equal the inside of my more complicated part. So maybe I'm going to say let u equal the square root of x, because that's the inside of my ln function. Well then my derivative, my du dx, ends up being a 1 over 2 root x. 1 over 2 root x. That's my derivative of the square root of x. Okay, well then solving for dx, I get that it's equal to 2 root x times du. Okay, so now let's substitute that in. So I would then have the integral of ln u divided by x times 2 root x du. Okay, so there's a little bit of cancellation here. I end up with the integral of ln u times 2 divided by root x du. And so this is not that big of a problem because we can rewrite this as ln of u over u times 2 du, right? Because we know that root x is actually equal to u. But the problem is that I still have no idea of a function that has that as its derivative. So I still can't find the antiderivative. Right? If you ask me what function has derivative ln x over x, I don't know the answer. So this tells me that, okay, maybe my choice of u wasn't that helpful. You know, I ended up with something that doesn't seem any better. So what I'm going to do instead, and it's going to be hard to fit on the page, I'm going to do my best here. So instead, I want to let u equal the entire complicated part. So I'm actually going to let u equal ln of root x. If I take its derivative then, du dx, what I get, okay, well my derivative of ln is going to be 1 over root x, and then I want to multiply it by the derivative of the inside, which is 1 over 2 root x. So I actually end up with 1 over 2x as my derivative, because the root x times root x becomes an x. So then solving for dx, I get that it's equal to 2x du. Okay, so now let's try this in my integral. I'm now going to have the integral of u, because our entire u is ln of root x, so that entire numerator is my u. I still have an x in the denominator, and then for dx, I plug in 2x du. Okay, well now this is better because my x's are going to cancel directly, and so I have the integral of 2u du. So now we just need to find the antiderivative of 2u. Well, that's just the power rule again, so that's going to become 2 times u, and we increase the power by 1, so it's u squared, and then we divide by the same exponent, so divided by 2 plus c. We can simplify that a little bit. Those 2's are going to cancel out. And then all that's left to do is to write our final answer in terms of x. So it's u squared, where our u is this ln of root x. So it's ln of root x squared plus c. And so that's our final answer. And again, you should check the answer while you're just starting out. And the way that you check it is you just take its derivative and see if you get the original function back. Okay, so question, how do we use substitution if we have a definite integral? So what if there are bounds on the integral? What do we do to account for it? And so the answer is that we need to change the bounds on the integral to be in terms of u. Everything else is the exact same as doing u substitution on an indefinite integral, because remember, when we're finding a definite integral, when we're finding that signed area, we actually first have to find the antiderivative of the function anyway. So we're going to be using the same method. However, we do need to change these bounds because the bounds on the integral at the start are for x. That's saying that x is traveling, for example, in example 1, x is traveling between -1 and 1. So depending on our choice of u, it may be traveling between two different numbers. So let's try to work through this example here. So we have the definite integral from -1 to 1 of x cubed times 1 plus x to the 4 all cubed. So we want to let our u, we're going to use the same sort of strategy to choose u. So we want to let u be the inside or the exponent of the more complicated part. Well, the more complicated part of this function is this 1 plus x to the 4 to the power of 3. And so we want to let u equal the inside of that. So this is going to be 1 plus x to the 4. So then when we find du by dx, our derivative of u with respect to x ends up being 4x cubed. And then solving for dx, we get that it's 1 over 4x cubed du. Okay. So with indefinite integrals, that would be enough to then substitute into our into our integral. So we would have, x cubed times u to the power of 3, and then our dx would become a 1 over 4x cubed du. And, everything would be looking great because those x cubes cancel. But the problem is I have these bounds here that I need to deal with. I can't just ignore them. And if I write -1 to 1, I would be wrong. So don't write -1 to 1. Okay, that's not correct. So what I usually do is in the same step as my choice of u, I also off to the side write bounds, and I deal with changing the bounds right at the beginning. So my original bounds were -1 to 1, so I need to figure out what does u equal when x is equal to -1, and what does u equal when x equals 1. So when x is equal to -1, u, which is equal to 1 plus x to the 4, is going to equal 1 plus -1 to the power of 4. Oops, that's supposed to be a 4. Okay, so then my u of -1 is going to be 1 plus 1, so it's going to be 2. My next bound, which is u of 1, so when x is equal to 1, u is 1 plus 1 to the power of 4, which is also equal to 2. So my new bounds are actually going from 2 to 2. And what's one of the first properties of my definite integral? So if I have an integral going from the same number to the same number, that's talking about the area underneath a single point. And so without even trying, I know that that is going to be 0. So you may be wondering, well, what does that mean? Like, how do I get an area of 0? Well, remember, this is a signed area. So what this is actually saying is we have a symmetric function here. And so it's equal parts negative area and equal parts positive area. So that's what's happening in this question. That's why we got an answer of 0. Okay, but the important thing to highlight in this example is just, we changed the bounds and we proceeded with u substitution the same way as before. So let's work through another example. So there's lots of space on that page. Okay, for our second example, we have the integral from 0 to pi over 2 of 1 minus cosine of 3t times sine of 3t. So first thing we need to do is choose u. And so, okay, we have to decide what's the more complicated part of this integral. Is it the 1 minus cos 3t or the sine t? Well, I would say that just slightly, this 1 minus cos 3t, this is a little bit more complicated than sine of 3t. So I'm going to let u equal 1 minus cosine of 3t. And so then my du dt, this time, because it's not an x, my du dt is going to equal, so my derivative of negative of 1, sorry, we'll start there. My derivative of 1 is 0. My derivative of minus cosine of 3t is going to be minus minus sine, so positive sine of 3t times 3 because of the chain rule. So solving for dt this time, right, that's sort of my equivalent of dx, I'm going to get 1 over 3 sine 3t du. Okay, I also want to deal with the bounds because it's a definite integral. So I need to figure out what u equals when t is equal to 0. So when t is equal to 0, u, which is 1 minus cosine of 3t, is going to be 1 minus cosine of 0, which is 1 minus 1, which is 0. So it turns out my first bound doesn't actually change at all. It's still 0. If I want to figure out what u is when t is pi over 2, I take 1 minus cosine of 3 pi over 2. Oops. That doesn't look like a 3 pi over 2. Let's try to write this again. So we get 1 minus cosine of 3 pi over 2. There we go. And cosine of 3 pi over 2 is 0, so this is 1 minus 0, which is 1. So my new bounds on my definite integral are going from 0 to 1. Okay, so now let's plug our substitution in. Well, this first piece, this 1 minus cosine 3t, becomes a u. And sine of 3t, we don't do anything to it, so we're just going to keep it there for now and hope that it cancels. And then our dt, we know that that's equal to 1 over 3 times sine of 3t du. Okay, well, we can cross out. Those sine 3t's are going to cancel, which we're happy about. That's a good sign. I'm going to actually take that 1 over 3 and pull it out in front of the integral, just to make our lives easier. And then I'm left with the definite integral of u du. And so again, I can just use the power rule on this. So my antiderivative is going to be u squared to the power of 2. And remember, we still need to evaluate it between 0 and 1. So simplifying this a little bit, this is 1 over 6 u squared evaluated between 0 and 1. And so you might be tempted at this point because when we had indefinite integrals, at this stage we would plug back in our choice of u. So we would be plugging back in that 1 minus cosine of 3t. But we don't need to do that here because we just need to evaluate this integral, and we know that the bounds of u go between 0 and 1. So I don't actually need to plug back in my choice of u. I can just directly evaluate between the bounds for u. So it becomes 1 over 6, 1 squared, so we plug in the top bound first, minus 1 over 6, 0 squared. And so our final answer is just 1 over 6. That's our signed area. And so if I had chosen to plug back in my 1 minus cosine of 3t in for u, I would actually have to change these bounds back to the original bounds of 0 and pi over 2. So if I were to change that u back in terms of t, I would also need to change my bounds back in terms of t. But that ends up just being way more work, and you've already actually done the work over here when you computed the new bounds. So this is the work that allows you to avoid plugging back in at the end, is because you've already computed the bounds. Okay, so let's work through a few more examples just to try to really solidify the technique of substitution. And so we'll be switching back and forth between indefinite and definite integrals just to try to make sure we're used to both. So this next example, we're working with an indefinite integral because there's no bounds on the integral. And so this kind of looks like a complicated thing. We've got an e to the x and a 1 plus an e to the 2x. And so, I don't know, your first choice of u, at least my first choice of u was wrong. So I want to show you what happens, because it's no big deal if you choose the wrong u. You just have to know how to recognize it and how to fix it. So I started off by saying I think u is the denominator. 1 plus e to the 2x. Okay, well, if I take its derivative, du dx, what happens? Du dx ends up being, well, what's the derivative of 1 plus e to the 2x? It's going to be 2 times e to the 2x. So then dx ends up being 1 over 2 e to the 2x du. Okay, so let's plug that in our substitution and see what happens. I get e to the x on the top. On the bottom I have u. And then for dx I have 1 over 2 e to the 2x du. And so one of my e to the x's on the top cancels out with one of the e to the x's in the bottom, but I still have an e to the x there. So that's no good. So there's still x's involved with this, and it's not easy for me to replace that e to the x with a u. So that tells me that I've actually chosen the wrong u, and I should start again. I should choose something else. So what's another option? I guess e to the x. That's really my only other natural choice. So I'm going to let my u be e to the x. My du dx then becomes also just e to the x. The derivative of e to the x is just itself. And then solving for dx, I get that it's 1 over e to the x du. Okay, let's try plugging this in now. So I get the integral of u over 1 plus, oops. Well, okay, I have 1 plus this e to the 2x. Well, e to the 2x, sorry, I can't seem to write a plus sign there. E to the 2x is actually just e to the x squared. So I actually have a 1 plus u squared in my denominator. Now for dx, I have 1 over e to the x du. And so you might be like, oh no, we still have an e to the x there, but remember, our u is actually e to the x. So we're actually fine here because that e to the x is just a u. So we end up with the integral of u divided by 1 plus u squared times 1 over u du. And so we have some cancellation, and I have just the integral of 1 over 1 plus u squared du. And so here is where your knowledge of inverse trig functions comes in handy. So you now need to think of, okay, can I think of a function that has derivative 1 over 1 plus u squared? And hopefully this is the most popular one. Hopefully you recognize this as tan inverse or arctan. So we know that the derivative of arctan of x is 1 over 1 plus x squared. So the derivative of tan inverse of u is 1 over 1 plus u squared. So we add the plus c, and that's my antiderivative. Now, because this is not a definite integral, it's an indefinite integral, I want my final answer to be written in terms of x. So all that's left to do is to plug back in our choice of u, which is e to the x, and we have tan inverse of e to the x plus c. And you could check your answer by taking the derivative to make sure that you get back to the original function. So this is a good example that shows that, you know, my instructions for how you choose u are almost always going to work. But once in a while you're going to get a weird function and the choice of u is not obvious. And so you need to be comfortable with choosing the wrong u and how do you correct it. And really what it is don't erase your work, you know, keep what you've written down, keep what you've done written down, because it's good to sort of see what you did and what went wrong. But then just choose a different u and start again. And there really aren't ever very many choices to choose from. And so you'll be able to get to the answer, just don't get flustered. Okay, so example 2, which is our second last example. So, okay, now we have a definite integral again, so we're going to have to deal with the bounds. And we have x times x squared plus 1 to the power of 1/3. So definitely no question, the more difficult part of this function is going to be the second part, that x squared plus 1 to the power of 1/3. And the sort of rule of thumb for how we choose our u says to take the inside of the more complicated part. That should be our first sort of attempt at choosing a u. So the inside of our cube root is this x squared plus 1. So I'm going to choose that as my u. Then du dx, my derivative of u with respect to x, is going to just be 2x. Solving for dx, we get 1 over 2x times du. And we need to deal with the bounds because it's a definite integral. So we see that x traveled between 0 and root 7, so we need to see what u does at 0 and u does at root 7. So u of 0 is going to be 0 squared plus 1, which is just 1. And u of root 7 is going to be root 7 squared, which is just 7, plus 1, which is 8. Okay, that is not easy to read. 7 plus 1. Okay. So my new integral is going to be going from 1 to 8. And plugging in my substitution, I still have x, but now inside the bracket, that's what we've called u, and it's u to the 1/3. And my dx is 1 over 2x du. And so now, thankfully, those x's cancel, and so I'm just going to clean up my integral a little bit here. So I'm going to pull out that 1/2, and we now have the integral from 1 to 8 of u to the power of 1/3 du. So once again, this is reduced to another power rule. So all that I need to do here is apply the power rule to my u to the 1/3. So my antiderivative becomes u to the power of 1/3 plus 1, which is 4/3. And we're going to, divide by 4/3 as well. So divided by 4/3. It's hard to write a 4. Now I'm trying to be a perfectionist with the stylus pen, and it's backfiring. Okay, so we have that, and it needs to be evaluated between 1 and 8. So before I do the evaluation, I always like to clean up my integral a little bit. So this is going to become 3 over 8 u to the 4/3. Notice I'm not putting the plus c. The reason I don't need to put the plus c is this is a definite integral, so those plus c's would cancel. My answer is going to be an area. And now at this point, again, I could either plug back in my u, which is the x squared plus 1, which means I have to go back to the original bounds of u and 0 and root 7, or I can just take advantage of the fact that these bounds here, this 1 and 8, are for u. So I can just evaluate in terms of the u bounds. And so if I do that, I get 3 over 8. We plug in the top bound first, so that's 8 to the power of 4/3. Minus, then we plug in the bottom bound. So it's going to be 3 over 8 times 1 to the 4/3. Okay, so working this out, you could use your calculator. I'm going to try to use my brain here. We'll see how it goes. So I have 3 over 8. This 8 to the 4/3, this means I take the cube root of 8, which is 2, and then I raise it to the power of 4, which is going to be 16. And then I subtract 3 over 8 times, well, 1 to the power of 4/3 is just 1. So I end up with an answer which is 45 over 8. And so that's my final signed area answer. Okay, one more example to go, and it's another definite integral. So we want to find the integral from 0 to 1 of this complicated looking function here. So we have 10x to the 4 plus 6 divided by x to the 5 plus 3x plus 2. So if I were to try to choose my u at the beginning, I would say that the denominator looks slightly more complicated. So I'm going to pick u equals x to the 5 plus 3x plus 2. When I take its derivative, du dx, I get 5x to the 4 plus 3. And so dx ends up being 1 over 5x to the 4 plus 3 du. And so keep in mind, when you're trying to sort of evaluate whether or not your choice of u is a good one, your dx here, like your thing multiplied by the du, you want to have that help you cancel the remaining x terms that are in your integral. So we want this 5x4 plus 3 to cancel with that 10x to the 4 plus 6. So that's sort of what we're hoping it will do, and it turns out that it will be able to. But before we do that, we want to deal with the bounds. And so we need to figure out what u of 0 is. And so u of 0 is going to be 0 to the power of 5 plus 3 times 0 plus 2. which is just equal to 2. And u of 1 is going to be 1 plus 3 plus 2, which is going to be 6. And so we end up with, I'm just going to write it down here since we have lots of space. So we end up with the integral from 2 to 6 of 10x to the 4 plus 6 over u times 1 over 5x to the 4 plus 3 du. And okay, so one thing I just want to say before we continue with this example is you need to be careful when you're changing the bounds. Let's say hypothetically that u of 0 came out as 20. So if u of 0 was 20 and u of 1 was 6, you might be tempted to write your bounds as the integral. So I'm just going to write down what I'm saying, but I'm going to erase it. So let's say your original bounds were 0 to 1, and you found that u of 0 is equal to 20, and u of 1 is equal to 6. Your new bounds, you might be tempted to write 6 to 20. Oops, 6 to 20, but that would be wrong. Okay, so it's not that the smaller bound has to go on the bottom. It's that whatever, so your u of 0 should replace the 0, and your u of 1 should replace the 1. So how you would want to write your new bounds in terms of u is you would actually still have, the 20 on the bottom and the 6 on the top. Okay, so just be careful when you're changing your bounds that you're putting them in the correct spot, regardless of whether or not which number is bigger and which number is smaller. You should be just placing, u of 0 wherever 0 was, and u of 1 wherever 1 was. Okay, so that's just something that I wanted to say there. I'm going to erase this because that sort of looks weird. It didn't happen in any of these examples, but it can happen. So I wanted you guys to see this in case it comes up on MyMathLab. Okay, so we're working with this integral here, and we were hoping that our x terms are going to cancel out. Well, looking at the top, it's actually very close to what we have on the bottom there. It's just multiplied by 2. So we can rewrite this as the integral from 2 to 6, and you can rewrite the top as 2 times 5x to the 4 plus 3 divided by u times this 1 over 5x to the 4 plus 3 du. And so now those 5x to the 4's plus 3's cancel, so that gets rid of all of our x's. I'm going to pull out that 2 in front of our integral, so we have 2 times the integral from 2 to 6 of 1 over u du. And we know which function has derivative 1 over u. It's our ln function. So our antiderivative of this becomes 2 times ln of the absolute value of u, and we want it to be evaluated between 2 and 6. So plugging in our top bound first, we get 2 ln of 6. I'm going to drop the absolute value sign here because we don't actually need it. 2 and 6 are both positive. And it's minus 2 ln of 2. Now, just in case MyMathLab asks you to do something like this and you have to fully simplify your answer, my claim is that this is not fully simplified. If they want an exact answer that's fully simplified, this would be wrong. So I would start by factoring out the 2, and that would leave me with ln of 6 minus ln of 2. Okay, well, let's remember our rule for ln of a divided by b is that it's equal to ln of a minus ln of b. So right now we have ln of a minus ln of b. We know that we can rewrite it as a over b. So this becomes 2 times ln of 6 divided by 2, which is just 2 times ln 3. Okay, so an exact simplified answer, this is where you would leave it. Okay, if they wanted a decimal answer with rounding, then you could have done it, back here at this step. You could have used your calculator at that step in order to find your decimal answer. But otherwise, you've got to remember your logarithm tricks. Okay, so that is it for this section, and I guess that is it for the course. Thanks very much for listening, and I guess you'll be hearing from me on Course Basis soon enough.